Hello, welcome to session number 2 in the series Microwave and Millimeter Wave Circuit Design. My name is Anurag Nigam, and last time we had seen Maxwell's equations as cause and effect equations, and we had a point form and integral form of Maxwell's equations. So I'm going to repeat here the point form of Maxwell's equation. It says curl of H, which is basically a loop of H, right? Curl of H is going to be equal to a determinant of a matrix, which is going to be X, Y, and Z is the unit vector, and then you have dou by dou X, dou by dou Y, and dou by dou Z, and then you have got Hx, Hy, and Hz. Now this is going to be equal to Js, which is the current density, and if you follow the right hand thumb rule, right, then whatever is the direction of the fingers, that would be the direction of H, and the cause of that loop of H is Js, which is pointed by the right hand thumb, right? So Js plus dou d by dou t. Okay, so basically this is a time varying component, right? So this is time varying component, while this one is the charge. So in a charge free medium, I can assume this to be 0, correct? And let's say if I consider a sinusoidal function, then everything can be expressed as e raised to j omega t, right? So then what I will do is I will have a j omega because of the differential, right? And then this will be d is equal to epsilon e, correct? Okay, so now if you consider any point, okay, any point has got, let's say, x, y, and z. Okay, so we can have ex component along x, ey component along y, ez component along z. Similarly, we have hx along x, hy along y, and hz along z. Now in this case, I am going to have a very specific case where I'm saying that the wave is propagating along z-axis. That means hx, hy, hex, and ey, okay, if they vary, okay, so they will be varying along z, not along x, not along y. Why? Because you need a charge for doing that variation, right? And then this is a charge free medium, so this doesn't happen, right? Now I'm considering propagation along z, then the orthogonal components are going to be hx, hy, ex, and ey. That means that the hz and ez component, they are going to be 0, right? So let's see what this equation reduces to under this situation, right? So I can write the expansion as dou hz by dou x minus dou hy, sorry, dou hy by dou z, right? So this is that term, right? So that's that term. This is x component plus. So let me make sure I'm recording. Yes, I am. Okay, so this would be that component. So let me just remove overwriting. I don't like overwriting. Okay, so that's there. Then the x term, y term is going to be, because of the cofactor, right, being minus, so you're going to have dou hx by dou y, right? And then you are going to have minus of, sorry, the dou hx by dou z, minus of, so this will be this cross term and this cross term, dou hz by dou x times of y, plus there will be another term here which will be dou hy by dou x minus dou hx by dou y times z. So this is going to be that term. So in this case, I told that z component is gone. So this z component is gone, this z component is gone, right? And then there is no variation along of x and y along x and y, because this is a charge free medium. So this entire term is 0, right? So I'm left with only minus of dou hy by dou z x plus of dou hx by dou z y. This would be equal to, so again the z component will be gone because of what you see on the left hand side. So collect the components of, so that is going to be j omega epsilon, right? Ex will be along x-axis and j omega epsilon ey would be along y-axis, correct? So that's that part. Now if I was to collect the terms, I would have an equation dou hy by dou z is equal to minus j omega, sorry for typing mistake, minus j omega epsilon ex, correct? This is going to be the term of x. Then I would have dou x hx by dou z would be equal to j omega epsilon ey, right? So now this is one set of equation. Okay, let's look at the other set of equation, which is going to be the other curl equation. So what is the other curl equation? The other curl equation is the loop of E, right? The loop of E would be the curl of E minus ms. So minus ms term is gone, right? Because there is no magnetic current. Minus dou b by dou t, right? Now let me see, put here direction. Yeah, dou b by dou t. Now b, again if you do a this thing, it will be minus j omega mu h, right? So now again I would have the same constraints, right? Because this is symmetric, I should be able to directly write them, right? So I would have the equation as dou ey by dou z x plus dou ex by dou z, that will be y, should be equal to minus j omega, right? So it will be minus sign, right? So it will be minus j omega mu hx, this will be x term, and minus j omega mu hy, and this will be y term, right? Again collecting the terms, I would have dou ey by dou z should be equal to j omega mu h x, and the other term will be dou ex by dou z should be equal to minus j omega mu hy. Okay, so now this is the other set of equation. Okay, now if you remember, I told you let's consider a case I'm looking at ex, which will be along x-axis, and hy, which will be along y-axis, correct? So this will result in, so if E collapses into H, then the propagation is along Z, right? So this is, let us consider that situation. So let's look at Ex over dou Ex by dou Z. So in this case, I will pick up this one, dou Ex by dou Z is equal to minus j omega mu hy, right? And if I do a second derivative, then I will be having this term. Now I will substitute dou hy by dou z from the left side equation, so that will be minus j omega epsilon. So I have, sorry, so I would have dou 2ex by dou z square would be equal to j. So now keep in mind, what do you have to keep in mind? J is multiplied with j, right? So hy, yeah, j is multiplied, so minus sign, right? And the two minuses signs are cancelling, right? So I am left with minus sign, minus omega square mu epsilon ex. Okay, so this would be minus omega square mu epsilon ex. Now let's represent omega square mu epsilon as gamma. Okay, so this is called a propagation constant. Propagation constant. Correct? So this is propagation constant. Okay, so now with that I have this equation as dou Ex by dou Z square plus gamma square Ex equal to 0, right? So that is one equation. Okay, so let's look at the Hy component. So for Hy I'm going to take this one. So dou Hy by dou Z. Okay, so dou Hy by dou Z is equal to j omega mu Hx. Am I right? No, it will be minus j omega epsilon Ex minus j omega epsilon Ex. And if I do another derivative, it will be dou Ex by dou Z. And if I take dou Ex by dou Z from here, it is minus j omega mu. So minus minus cancel. It will be omega square mu epsilon times of Hy. Correct? So dou 2 Hy by dou Z square is equal to that. Or it can also be written as dou 2 Hy by dou Z plus gamma square Hy is equal to 0. So this is equation number 2. So I am considering one situation, which is this. Now you can work with other situation which causes the propagation in Z direction. That is going to be Ey and minus Hx. So another propagation in same direction would be due to Ey and minus Hx. Okay, so Ey collapsing in minus Hx will also cause the z-directed wave. So I'm just solving for one of the solution, and the other solution is straightforward, Ey minus Hx, right? So let's look at Exhy. Okay, solution. Now if you look at the equation 1 by inspection, you can write the solution. So you can write the solution as Ex can be written as magnitude Ex e raised to minus j y z, and there is another component Ex e raised to j gamma z. So this is going to be the solution for equation number 1, right? Now the way it can be considered is, so let's look at another thing. Another thing is, if I was to do dou Ex by dou Z, then this will be equal to minus j gamma Ex e raised to minus j gamma Z plus j gamma Ex e raised to j gamma Z, right? And this term, if you see, is dou Ex by dou Z. That will be minus j mu Hy. So this will be minus j mu j omega mu Hy, right? So minus j omega mu Hy. So from here I don't have to write the equation for Hy as a solution for equation 2. I can directly get it over here. Hy is equal to minus j would cancel throughout, right? So I'll be left with omega mu divided by gamma, right? Ex e raised to minus j gamma z minus Ex divided by j cancel, right? And you will have omega mu by gamma e j y z. Okay, now so these are the two solutions for the two equations. This is a set of solution which refers to one of the wave which is traveling forward as well as backward. So the forward traveling component is this. So this is a forward traveling component along z, and this is going to be the backward traveling component. Okay, so when you consider backward, you consider from the source as minus z, right? Now gamma is called propagation constant. This would be beta minus j alpha. Okay, now beta is the propagation constant, and so beta is propagation constant. Okay, and alpha is attenuation constant. Correct? So now if I do that, then I can write Ex is going to be equal to magnitude of Ex, correct? E raised to, substitute that over there, you will have minus gamma z and cos of omega t minus beta z, right? And the second component will be Ex e raised to this cos of omega t plus beta z. Now let me tell you how to read this. Okay, again you can also write here h y is equal to Ex divided by omega mu y gamma times of E minus f z cos of omega t minus beta z and minus of Ex e raised to alpha z by omega mu by gamma cos of omega t minus beta z. Okay, what it says is you will have a Ex component and Hy component. So Ex component and Hy component, this will result in a wave this way, and this is positive z, so this is z0. Now Ex with minus of Hy, right, will cause propagation in this direction, so this is a minus z case. So if there is a source at origin, it result in two waves. One wave will go in positive z direction, the other wave will go in the negative z direction. So this is going to be the positive z direction and this is going to be the negative z direction. So you understood how the propagation is taking place. So Ex with minus Hy and will cause around minus z direction, and Ex with Hy will cause the wave to be along the plus z direction. So that's all you got to understand. Now the next thing is Ex over Hy, okay, or Ex over minus Hy. That would be equal to omega mu by gamma, correct? Now let us assume, so how is it going to be? These waves are going to be this way. So let's consider the forward traveling wave, right? So the forward traveling wave, if there is a alpha, okay, so this will cause the E wave to keep attenuating as it goes along z direction, right? So this is what is happening to E, and to H it is the same thing, but in the another plane, right? So this is going to go this way, so your axis is along here, right? So this is going to be along y axis, so you can imagine that, right? As we have seen in the earlier case. Like, so if you remember, I told you this something this orthogonal, right? So we are looking at the TEM wave here, right? So this is that, and same thing is happening on the other side. So I can always do this. Sorry, I can always say that the same thing is going to happen the other side. But sorry, oh, but this is kind of reversed like that. You understand? So this is kind of reversed like that, and it is traveling in this direction, right? So now you can understand what's going on. Sorry, wrong choice. Okay. So both are attenuating. Okay, as per minus alpha z on this side, e raised to, and as on this side it is going to be e raised to minus, means e raised to minus alpha z also on this side, because it is minus z, right? And again, the propagation, okay, beta is causing delay this way, and minus beta with minus z is causing delay the other way, right? So basically beta is the propagation constant, and alpha, sorry, beta is the phase constant, and alpha is the attenuation constant, and both comprise what is called propagation constant, right? Gamma. Okay, so you understood how if there is a source at origin, okay, how the ex and hy, and how ex and minus hy are going to be the two waves traveling in two different directions, right? Now let's look at the condition. The condition gamma is equal to beta minus j alpha, and let's say alpha equal to 0. So this is a lossless medium. In a lossless medium, alpha is going to be 0. So then if I look at the equation, ex would be equal to magnitude of ex, right, e raised to, so it is minus j beta z plus magnitude of ex j beta z, and then hy is going to be equal to hy is going to be ex by, sorry, let's do this clearly, ex by omega mu by gamma. So in this case gamma will be beta, right? So the gamma would be in this case beta e raised to minus j beta z, and then minus of ex divided by omega mu by beta, sorry, omega mu by beta again, and e raised to j beta z. Okay, so these are the ex and hy components. Now this ex by hx or ex by minus hy, right, is going to be omega mu by beta, and beta, right? So okay, so beta, okay, so basically gamma is equal to beta equal to omega square, sorry, root of, so it will be omega root of, so let's say where is gamma, so this is gamma, right? Right, so now this will be omega root of mu epsilon, so this will be by omega root of mu epsilon, correct? So now this results in root of mu over epsilon, so that is equal to z this is going to be the wave impedance z. So now what do we have? We have defined that the wave impedance z is equal to root of mu over epsilon in case of a lossless charge free medium, in lossless charge free medium. Okay, so this we understood. Now the next thing to understand is, if you remember the very first this thing, okay, we talked about something called phase velocity over here, right? So now we are going to look at what that is going to be. Okay, phase velocity is the velocity with which so phase velocity is velocity with which velocity with which a constant point, a constant phase point, a constant phase point moves in space. Phase point moves in space. Correct? Now, so let's see what that is. So we know that the phase is given by that. Correct? So if this is going to be constant, then if I take a derivative with respect to time of this should be equal to 0, right? So what do I have? I have omega minus beta dou z by dou t is equal to 0. Then this dou z by dou t is nothing but phase velocity Vp. So I have Vp is equal to omega by beta. So this is another equation which you should remember, right? And we also know that beta is equal to omega root of mu epsilon, right? So then this term would be equal to 1 over root of mu epsilon. Now you see that the phase velocity is also independent of frequency, right? Okay. So you see the phase velocity is independent of frequency. Okay, so this is a dispersion free medium. That's why this is what you're seeing, right? The phase velocity is independent of the frequency, right? And this can also be written as c0 divided by mu r epsilon r, right? Now let's also define what is wavelength. Okay, so now this is basically phase velocity. Let's mark it down. So this is phase velocity. Now I'm going to talk about wavelength. Sorry. Wavelength lambda. So the two nearest points which are in the same state of oscillation, right? They are going to be apart by 2 pi, right? So if I was to do b omega t minus beta z minus of omega t minus beta times of z plus lambda, that should differ by 2 pi, right? That should delay by minus 2 pi, right? So that would result in beta lambda equal to, is it right? Oh, I don't need a minus sign here. So I have got this subtracted from that. So this cancels, sorry. So this cancels and this cancels with this, and the signs basically are taken care of. So what is left with is going to be this equation, right? Okay. So that means lambda is equal to 2 pi by beta. Now this is another equation which you should remember. So if I look at this equation, this one, or rather this one, and if I look at this one, I can say Vp is equal to omega by beta. Omega is 2 pi f and beta is going to be beta, right? So 2 pi by beta is equal to lambda. So that is the famous relationship. Vp is equal, velocity is equal to wavelength into frequency. Okay, so this is going to be wavelength into frequency. This is another thing which you have to remember. Correct? So these are the basic relationships from here. And the solution is very simple, right? So this is for lossless charge free medium where alpha is equal to 0. Otherwise, you know, there is attenuation on left and right. Okay, now something similar happens if there is a voltage and current waveform, right, on a transmission line. So the reason I'm going to derive the two together in this session is that that is the basis for lot of circuit design. So this is going to be in the, basically this is propagation in the free space. Now if there is a propagation along a trace of metal, okay, which is called a transmission line, then there's a separate set of equations, right? So let's call that equations as telegraph equations. Okay, so what are telegraph equations, right? So uh, let's say if I was to draw equivalent of a line, so a line would have a certain resistance R over a distance delta Z, and certain inductance L over a distance delta Z. Then it is also going to have certain capacitance over a distance of delta Z, and then it is going to have certain conductance, okay, G also over delta Z. Okay, so I can consider line to be made up of repeating sections of this, where this distance over here is delta Z, right? So now let us write this. So let's say the voltage over here is V plus delta V, right? So voltage over here is V, so it is dropped, so delta V is negative. Okay, similarly, let's say the current here is I plus delta I, and over here the current flows out is I, but the current which flows in this branch is delta I. So the total current is I plus delta I. Again, delta I is negative because the current is going down. As the voltage is going down, current is also going down. So I can write here this way: delta V is going to be equal to drop across this RC, and that will be negative R plus j omega L times of delta V by delta Z should be equal to this thing times of I plus delta I, the current flowing through here, I plus delta I. So this is one equation. Next equation is delta I would be equal to, so let's do this, delta I would be equal to this current through G plus JZ, right? So that would be written as V times of G plus j omega C, but then it will be minus because it is decreasing, right? So these are the two equations. Now I can assume that this component is very small, so I can write this equation as dou V by dou Z is equal to minus R plus j omega L times of I, and dou I by dou Z is minus G plus j omega C times of V. Now if you see this equation and this equation, it would remind you of the same equation over here. You see here the same equation, so the solution will also be the same, isn't it? Okay, so now what I can do is I can write the equation dou 2v by dou z square is going to be equal to R plus j omega L into G plus j omega C times of V. So I just did that, and I can write the same for the other one, but I don't need to derive it. I know how to do that with a shortcut. So this is of this form, minus this is square. So this basically is going to be equal to R plus j omega L G plus j omega C, right? So then the equation is of this form, and the solution of V will be magnitude of V e raised to minus gamma Z plus magnitude of V e raised to gamma Z. Now if I was to do dou V by dou Z, then this will be gamma times of V e raised to gamma Z, and plus V, again it will be gamma here e raised to gamma Z, right? It's just that the j is not there because the j is absorbed inside this constant, right? So now I can say this is equal to the second equation, isn't it? Uh, Now, the first equation, right? R plus j omega L, isn't it? Yeah, yeah. So this can be written as R plus j omega L times of I minus. So I can write I as magnitude of V e raised to minus gamma z divided by R plus j omega L divided by gamma, right? Minus of magnitude of V e raised to gamma z divided by R plus j omega L divided by gamma. So now again there is going to be impedance here, which will be equal to R plus j omega L by gamma, which would be equal to root of R plus j omega L divided by G plus j omega C, isn't it? So this one is going to be the forward wave along Z plus Z, and this one would be a reverse wave along minus Z. So it's the same thing, right? And second thing is uh, you can write, so there is going to be little elaboration over here, and I will write it so that gives a lot of insight. Hmm. Okay, so I'm simplifying a lot of things here for you. It's just that when you read something, it can be along with the loss, and the loss can be dielectric as well as conductive, right? So these things which I am just keeping out of these equations, but you can always write it as in terms of 10 delta, right? So now uh, okay, gamma in this case, because there is the factor which is j is already absorbed. In the other case j was outside, right? So you can write this as that. Sorry, so earlier, because j was outside, that was why you get beta minus j alpha, but now the j is absorbed in it, so it is of this form, right? So that would be equal to root of R plus j omega L into G plus j omega C. Okay, another thing is, for a lossless case, R is equal to 0 and G is equal to 0. So this is for the lossless case. So in this lossless case, this will be equal to root of L over C, right? So that is going to be the impedance of a transmission line. So all you have to remember is this impedance equation for a transmission line, and there it is a propagation constant which will have attenuation constant plus the phase constant. Now you can do all kinds of mathematics. So if alpha was equal to 0, then it will be very simple. Beta would be equal to, now alpha is 0 when R equal to 0 and G is equal to 0, right? Then j beta, okay, so you will be left with j beta. Okay, so j beta would be equal to j times of root of, right? J beta is going to be j times, so j will come out, omega will come out. Okay, omega will come out and you will have root of LC. So beta would be equal to omega root of LC, right? And you can define the same way. Okay, Vp or propagation constant will be equal to the uh, will be equal to omega by beta. So in this case this will be equal to 1 over root of LC. So really the velocity of propagation along a line will depend on L and C's here, right? Okay, another thing is lambda, right? So lambda would be equal to omega by, sorry, 2 pi by beta, right? 2 pi by beta. The same equations will apply also here. Okay, 2 pi, sorry, this will be omega by beta, 2 pi by beta lambda. Okay, so beta is going to be equal to omega root of, so this can also be written as beta is equal to omega root of LC, right? Okay, so it will be again velocity is equal to wavelength into frequency. So we'll have the same equation here again. Velocity is equal to, sorry, again you will have the same equation by substitution. So let me write down here. Velocity is equal to wavelength into frequency, or wavelength is equal to velocity by frequency, or this can be also written as 2 pi by beta. So this is another equation which is of the same form, right? So this is for the lossless case. Now let us consider that r is not equal to 0, and also what you call g is not equal to 0. Now in general case I would have to write, okay, so I'm writing a general case with the loss. Alpha plus j beta is equal to root of r plus j omega l into g plus j omega c, correct? So now let me see how much time I have spent here. Sorry. Okay, I have spent 41 minutes, so I'm going to end this after this treatment. Okay, so now I can write this. Okay, let's consider this expansion 1 minus x raised to m. Okay, so this can be written as 1 minus mx plus m into m minus 1 times of 2 divided by 2 factorial times of x square plus m into m minus 1 into m minus 2 and so on, m minus 1 into m minus 2 divided by 3 factorial times of x cube plus and so on. So if I was to use this, okay, I have something raised to half. Now if I write alpha plus j beta of the form j omega root of LC, I take common, then I'm going to be left with 1 minus rg divided by omega square LC times of 1 plus j omega rc plus lg divided by rg minus omega square LC. Sorry, isn't it? Yeah, right. Okay, so now I can separate out, I can do the expansion of this term, right? Because if you see, okay, expansion of this term, and then I can substitute that in here, and then I can separate out real and imaginary. So I will get alpha and beta. So alpha would, if I collect real and imaginary, alpha would be 0.5 times of omega root of LC, root of 1 minus rg divided by omega square LC, right, times of w rc plus lg divided by, or omega square LC minus rg. Okay, a minus of, right, 0.625 omega root of LC. Now here you have to do a lot of derivation here to do this. This will be a cube term. Okay, omega rc plus lg divided by omega square LC minus rg, right? LC minus rg cube okay, because I have already done the expansion. Okay, so this is there, and so I should put another term here which was, I forgot, 1 minus rg over omega square LC. Okay, so let me write this clearly. So okay, now If I have editing tool, why not use it? No. So I forgot this term. Okay, so this is cube term and so on, right? So this is your alpha, and beta would be equal to, so now if you assume R and G to be 0, then these terms would disappear. Okay, so 0, right? Okay, if Rg is equal to 0, okay, so if Rg is equal to 0, then this terms will disappear, right? Okay, so this will cause alpha to become 0. So if R equal to 0, if G equal to 0, then alpha would become 0. Okay, so this is correct. Now let us consider beta. Okay, so the beta would be written as omega root of LC times of, again the same component, 1 minus Rg divided by omega square LC, right? Plus 0.125 times of this term, square term. So this is going to have even order terms, right? So this is going to be equal to omega root of LC times of this is a big term, right? Root of 1 minus Rg over omega square LC times of this term, omega times of Rc plus Lg divided by omega square LC minus Rg square. Okay, and so on. So all the even order terms will come here, and all the odd order terms will go there. Now, no matter what you do, the odd order terms will result in this R and G become 0, then all these terms are going to become 0. Now in this case, if Rg becomes 0, then you will see that these terms will become 0, but the first term is going to become 1, right? So if R is equal to 0 and G equal to 0, then beta is going to be equal to omega root of LC. And notice one more thing over here. Okay, that thing to notice is, okay, for a special case, the denominator, for example, okay, so if this denominator which you are seeing in these terms, right, so if this denominator Rg omega square LC equal to Rg, now that means omega is equal to Rg over LC, or F is equal to 1 over 2 pi Rg LC. Okay, so this is the frequency where attenuation constant will become infinite, isn't it? The attenuation constant let me see this again, omega square LC. No, it will become 1 minus 1 term, so this term will take it to 0, and this term will take it to 0, and similarly over here beta will become 0 because all these terms are taking it to 0. So in this case, if this condition happens, okay, then alpha is equal to 0 as well as beta is equal to 0. That means that transmission line has a frequency response, right? It's just that it is flat, but at this point Okay, this is going to have a propagation constant is 0. That means that it will not transmit anymore. So what it means is the following. Okay, what it means is the following. So this beta is a number which is function of omega, right. So if a frequency goes up, okay, so the beta will go up, right. So the frequency goes up, the beta goes up. Let me just, so I'm looking at frequency goes up, then beta goes up, and at a certain point beta will become 0. So we are talking at beta versus frequency. So at certain point beta will become 0, right, because at that point RGU is becoming equal to omega square LC. So then even a transmission line is a low pass circuit. So remember this, transmission line is a low pass circuit. So that is the thing which I wanted to derive from this all mathematics, right. So that is all you have to remember, right. And what else is there? Okay, so in the next section we will see, okay, so we know what is the impedance of a line. The impedance of a line for a lossless line, R equal to 0, G equal to 0, is root of L over C. Okay, so now we are going to talk about transmission lines, the physical transmission lines. So transmission lines, so all the transmission lines are going to follow this telegraph equations, right. So that is why I did this telegraph equations. And after that there are different forms of transmission line. So one is called a microstrip line. Okay, so what is in a microstrip line? So there is a ground plane, right, and then there is a substrate on top of it. So there is a substrate on top of it. Okay, so this is a ground plane. Okay, so let's draw this in blue. So this is your ground plane. So this is your ground, blue colored thing. Okay, so this is a ground plane. So this entire thing is a ground plane. Okay, and on top of it there is going to be a line like this. Okay, so there is a ground plane and there is a line on top of it. So this is called a microstrip line, right. And then you have another line which is called CPW, or coplanar waveguide, in which case there is a substrate, but unlike so let me draw a substrate. So there is a substrate like this. So okay, and then there is a line, let's say like this. So this is line, and then on the same plane there is this ground there, right, and on the other side also there is a ground there. Okay, so now on the top view it is going to look like this. There is going to be line, so on the top view it is going to be a line, and there are two ground planes like this. So this is a line and these are two ground planes. So this is called CPW. In case of microstrip, the top view would be a line and then there would be a ground underneath like this, right. Now there is one more which is called CPWG. So along with the coplanar lines there is going to be a ground underneath, so that will be called CPWG. CPWG. Now these are all planar lines, right. So these are some things which can be fabricated, for example, on PCB, right? Then there are going to be coaxial lines, right? So they are going to be coaxial lines. So for example, for your cable TV and all that, so this outer shield is a ground, right? And the inner shield is your line. So it is just the same thing as a microstrip line, but the ground is just wrapped around it. So there is a dielectric in between and the ground is wrapped around it. So all this substrate is a dielectric material. So this is called coaxial line. Okay, all these lines with two conductors, one is the signal line, other is the ground line. All these lines with two conductors are capable of what you called that, transverse electromagnetic waves, as we discussed till now, right? All these lines so have two conductors. That's how you are going to have C and G terms, right? Because there has to be a ground, right? So in a Telegraph equation, you see that there is a ground, right? So there's this ground. Okay, that means there has to be a ground and there has to be signal line, right? A signal line represents a series R and L, series resistance and inductance, and then there is a dielectric between ground and the line, which causes this C and G. Conductance is the leakage to the ground, and C represents the capacitance, because if you take two metal plates and separate by a dielectric, it will become a capacitor, right? So these lines basically are representative of telegraph lines, telegraph equations they follow, because they have two conductors. One is the signal, other is the ground, all of them, right? So they are governed by this telegraph equations. Now where does the L come from? The L comes from the how thin the line is. If you make a thinner line, the L is going to be larger. If you make a thicker line, the L is going to be smaller. How about R? R is the conductive loss. Now if you know, see, if there is a frequency involved, then most of the current is confined to the surface of a conductor, not in the center of the conductor, right? So this is also a derivation of Maxwell's equation only. I'm not going to derive it, okay? But there is something called skin depth. So higher the frequency, smaller the skin depth. So the current is confined on the surface of the conductor. So now that skin depth basically is deciding what is the cross-sectional area, and that is deciding the resistance. So R comes from that, L comes from the width of the line, right? And then C comes from the gap between the line and the ground. So if you make the substrate higher or taller, then C, you are reducing C. And that's way you can control the impedance of a line, because the impedance of the line we have come across is L over C. So if you bring the ground plane closer, you are increasing C. That means the impedance of a line will reduce. Or if you bring the coplanar grounds closer to the line, then the impedance is going to reduce. If you take them far away, the impedance is going to increase. Similarly, if you make the line fatter, okay, then L is going to reduce, so impedance is going to reduce. If you make line thinner, then L is going to increase and impedance is going to increase. So you see, it is all a question of play of L and C, which decides the impedance of the line. Now depending on which line you are talking about, right, microstrip, CPW, CPWG or coaxial, you can see it is just a play of L and C, and the propagation constant is going to be 1 over, so it's basically the speed, velocity is going to be 1 over LC, right? Vp is equal to omega by beta, and beta is omega root of LC. So omega cancels out, then you have only 1 over root of LC. So this is the speed. In case of free space wave, Vp was going to be equal to root of mu over epsilon, right? So they are similar in nature. That's why I discussed telegraph equations here, right? And it gives a lot of insight into what is going to be the impedance of the line and how to increase the impedance or decrease the impedance by changing the separation or making the line wider, right? So more about this in the coming session, where I'm going to discuss the same equations. I'm going to derive what is called a Smith chart, right? Once I derive a Smith chart equations, then you will be very clear about what is impedance matching. So I'm going to end this session here. Thanks a lot. Thank you.